Statistical mechanics is a branch of physics that uses statistical methods to deal with large populations of particles. At its core, it bridges the gap between microscopic, quantum mechanical behaviors of atoms and molecules, and macroscopic properties like temperature and pressure that we observe daily. First, let's talk about the fundamental concept, the microstate and macrostate. A microstate refers to a specific arrangement of all particles in a system, encompassing precise positions and velocities. Conversely, a macrostate is characterized by macroscopic properties like temperature, volume, and pressure, arising from numerous possible microstates. One pivotal idea in statistical mechanics is the Boltzmann distribution, which tells us how particles are distributed among various energy levels in thermal equilibrium. This leads us to the concept of entropy, a measure of the number of ways a macrostate can be realized through different microstates. Higher entropy means more disorder and more available microstates. Canonical and grand canonical ensembles help simplify calculations. The canonical ensemble considers a system in thermal equilibrium with a fixed number of particles, volume, and temperature. The grand canonical ensemble, however, also allows particle number to fluctuate, considering systems in both thermal and particle exchange equilibrium. Lastly, we use partition functions to derive important thermodynamic quantities. For a canonical ensemble, the partition function, denoted as Z, sums over all possible microstates, weighted by the Boltzmann factor EKT. By relating Z to free energy, we can calculate properties like entropy, pressure, and heat capacity. With these foundational concepts, you grasp the basics of how statistical mechanics explains macroscopic phenomena from microscopic behaviors. Like and subscribe for more videos like this.